So we have a fake switch data or fake bounce data from analog discovery. We put that data on the course website. You can download that. It is in the form of a CSV file, and I'll show you how you can import that data into Waveforms software and run it through the WaveGen. So this is, you have typically seen square wave and sine wave and triangle wave being generated by the analog discovery board, but we can also generate a custom voltage waveform, which we are going to do in this case. So if we do this right, our voltage waveform should look like this. So if you are looking at the screen, the project 3 right up screen, we are going to be generating a fake data that is essentially in a CSV file right now. We are going to import that, and it's going to look like this, where clearly um, those two instances are where the bounce happens, and that's the high state, that's the low state. So we are going to see if we can debounce this fake switch first. So our goal is going to be to obtain an output which stays high, goes low, and then stays low for quite a bit, and then comes back up high. So we need to get this information from the website. The link is uh, in your description, and I have already downloaded that to my computer, and I'm ready to generate that fake switch data. So before we actually get into all the details and use waveforms, let's talk about the protoboard itself and how that relates to our switch debouncer circuit. And as you can see, I'm just showing you how I came up with that. I just searched on Google switch debouncing circuit 555, and that was the first image that you saw. Uh, Come on, can you give me a clean? Okay, maybe this is good. So what we are going to do here is, okay, so perhaps a different one is going to be okay. Yeah, this will do. Okay, so I have uh, a switch debouncer circuit, which is essentially the same as what we have discussed before. R1 is 100K, C1 we talked about the design. It should be a 1 microfarad capacitor, and all the other things we addressed it. So switch, the bouncy switch goes to pin number 2, and the other end goes to ground. And I have picked out a switch, a push button that I'm using as a switch for experiment 3, and I'm showing you on the other screen. So if you look at that guy over there, that's your switch, and you can of course press on it. That's going to be your push button. So whenever you press it, I can hear a clicking sound. Perhaps you cannot, but that's your push button that we are going to use to debounce. So let's see. So that's going to go over there. But when we are using this fake data, we do not need that pull up resistor R2. So we are going to build this circuit with everything in it except for R2. And then we are going to measure the output on pin number 3 of the 555 timer. So as usual, I will talk about the circuit first and how it relates to the circuit diagram that you see, and then move on to uh, waveforms. Um, a quick question, is the light, does it make it better or worse? So this is one light and this is no light. So light versus no light, I am trying to take an opinion. No difference. Okay. In that case, I will just switch it on so that at least I can see. It's a gloomy day today. There's a lot of rain and clouds and not too much natural light. Okay, so let's talk about this. We have the 555 timer chip that is right in the middle of the board. The notch is point facing the left side. So we have pin number 1 here, 2, 3, 4, and then 5, 6, 7, 8 going on the top side. Pin number 1 has been connected to ground as suggested by the diagram here. Pin number 1 connected to ground. Then you have pin 2 that I have not connected to anything right now, because you see pin number 2 using this orange wire jumps to this point. So pin number 2 using this orange wire jumps to this point, but there is nothing connected over here. There are other orange wires that I'm going to be using later on. I'll just put them on the proto board to do the fake switch debouncing first. So pin number 2 right now is not connected to anything, it's open. And uh, I'm going to need to put a switch there, in this case a fake switch there. So I'm going to connect a yellow wire, which is my WaveGen, to pin number 2. Let me take a yellow wire here and then go into pin number 2. And once I do that, I'm going to have the fake, at least, I'm not giving it anything right now, but I know I'm going to need to use waveform analog discovery waveforms to give that custom fake switch data on WaveGen 1. Pin number 3, that's going to be my output. So let me put a scope channel there. Perhaps this is going to be my input, so I like channel 1 to be input. I'll put my orange wire, which is my scope channel, to be on pin 3. Pin 4 should be connected to VCC, the supply voltage. So pin number 4 goes to this purple wire here, jumps to that point, using another purple wire jumps to that point, and then red wire to connect it to high. So that's how pin 4 is connected to high there. Pin 5 needs to connect it needs to go to ground using a 0.01 microfarad capacitor. Pin 5, 0.01 microfarad capacitor. On the other end, there is a black wire going to ground. Pin 6, we have pin 6 and 7 connected together. I don't know if you guys can see this, but there's a small little jumper wire right in the middle there that is connecting pins 6 and 7 together. So I don't know if you can see it, but there is a small wire there. Then now that they are both the same point, I'm connecting pin 6 to high using a 100 kilo ohm resistor as suggested by the circuit. So 6 to high using R1 of 100 kilo ohms, that's right there. Pin number 7 is connected to ground using C1. We have found out the value of C1 to be 1 microfarad. So this is the 1 microfarad capacitor that the positive terminal is connected to pin 7, the negative terminal is connected to this point, which by using these two yellow wires is connected to the ground rail, which is the bottom rail here. So and then of course you have the pin 8 connected to high using that red wire there. So that's essentially how I put together the circuit. There is some blue wire here and a green wire there, and I didn't talk about those things yet. In fact, I don't need the blue wire. Well, let me just leave it there. I'm not using it for now. And I'm also not using this yellow wire for now. But as we move on with project 3 to the real switch, you will see all of these come into picture, come into play. Okay, so let's see. I've given the WaveGen. I've tried to measure well, let me measure the input on pin 2. So actually, I'll move the orange wire on pin 2, and actually, the output is going to be on pin 3. So I'm going to use a blue wire to be connected to pin 3. I misspoke earlier about orange wire being connected to pin 3. I want yellow, the orange to measure the input, which is the fake switch, and blue to measure the output, which is hopefully the debounced clean switch. And then of course I also need to connect orange white and blue white to ground, which I'm going to do. I can actually do it on the board here. Out a bit, and orange white going into ground as well. Let me use this ground here. They're all the same ground. Okay, so that completes the circuit as well as the wave gen, my scope channel 1, scope channel 2. So I think I'm in good shape in terms of the circuit for fake switch. So what I'm going to do now is minimize this window, bring up my waveforms window, and then I'm going to need to switch on the power supply because I need the plus 5 volt supply. I will have that. I'm going to connect, adjust that to 5 volts and turn it on. And then go to welcome. I need WaveGen, so I'm going to have that open. I also need scope, so I will have that window open. So for WaveGen, I need the fake switch data. So for that, I'm going to have to import that data first. So uh, in channel 1, I have an option drop down menu where I can select between simple, basic, custom, play, sweep, modulation, all those different WaveGen properties that I could select from. So this time I'm going to use custom because I have a custom file to import. Once I do that, it will give me an option to import the file. I'm going to click on import. I'm going to point to the place where I have my fake switch data. It's in a form of an Excel file. I'll open that, and once I open that, it is going to give me an option to be able to adjust the amplitude and offset and the frequency of the wave that I want to generate. So as per the write-up, I'm going to adjust those values to these, I believe, right? Frequency is 4 hertz, offset and amplitude to be 2 volts. Um, so I'm going to set offset to 2 volts. And amplitude also needs to go to 2 volts and frequency of 4 hertz. Okay, so this way I have a wave that goes between 0 and 4 because of amplitude 2 and offset 2, and that repeats every 4 seconds, 4 hertz, so quarter of a second. Say okay, so once I have that, it is going to show me in WaveGen what I have in terms of uh, the fake switch data that I want to run through this circuit. It is disabled right now, so let me enable it, run it. So it should be on, which means pin 2 of the 555 timer is getting that fake switch data. I'm going to go to scope and I'm going to turn that on to see. Okay, so I see a lot of things happening very quickly, so I'm going to have to adjust the time base here. So instead of 1 millisecond, I'm going to make it 100 times bigger. So I see several events happening. There is also noise on these channels. So remove the noise here and here. I am going to have to adjust the voltage. So let's see, make the voltage 1 volt per division here. There is a lot of noise. Uh, let's see if I make this offset Okay, I'm running the scope. I am running the supplies. The offset. Okay, so this is okay. However, 4, 5, 6, 7 connected to ground here, one ground here. Hmm, There seems to be some problem. Um, Brilliant. Okay. Uh, Turn the supplies off. Uh, I did not connect the ground wire to my analog discovery. Okay, sorry about that. It should now be clean, so I can turn the supplies on here. What else did I miss? Red wire, of course. All right. Hopefully now things will be okay. All right, we are in business. 2 volts offset. Bring this down a bit, and let me bring this down a bit just to make sure that they are aligned. Uh, and I can increase the plot width here to make it 3. And I can stop the acquisition for now. Okay, so there were a couple of things that I forgot to do, and I was trying to see if things work or not. The two things were the power and ground. Um, Once I did that, I was able to take a look at my fake switch data versus the output. So as you can see on this plot, the orange wire indicates the fake switch. I'm measuring that on pin 2, and pin 3 is a clean output because it's not allowing the capacitor to discharge very quickly, and it is going down just a little bit beyond where that bounces because we have used a capacitor of 1 microfarad. But ideally, you would want to make it tighter so you can in fact come back lower. So if I zoom in here to indicate what I mean, so this blue line right now is happening a little bit after all that bounce has finished. So if I were to bring it tighter to where the bounce is, I can do two things. One is reduce my energy consumption because it's on for less amount of time. But the problem with that is that I will be running very close to where the bounce is. So I might accidentally uh, not be able to do that debouncing efficiently. So there's a risk versus reward scenario there. Um, so if I go back to what I had originally in terms of my view, uh, that was it. Yeah, so that's your fake data versus the output that is clean and it is not going down. Of course, if I use a bigger capacitor or a bigger resistor, that blue line will stay on for a longer time. Um, and if I use a smaller resistor or a smaller capacitor, that blue line will come down uh, faster than what it is doing. So it will be a shorter pulse, which means that it will still do the bounce. Okay, so let me take a moment here and answer any questions regarding the uh, fake switch data. Okay, it looks like you guys are okay with the discussion so far. We will move on to the next step in project 3, which is remove the fake switch and actually go through an actual switch. So to be able to do the actual switch, we are going to have to adjust our switch based on this diagram over here. So the switch, which is the input which goes into pin 2, is pulled up to high using R1. And that is essentially done so that when the switch is pressed, your input is ground 0, and when the switch is released, your input will should read high voltage. Um, so let's do that, and I'll show it to you on the circuit as well. The circuit that we have been looking at is right there. So we are going to connect this R2 and an actual switch. So first things first, though, supplies turned off, wavegen turned off. Come back over here, remove the wavegen. I'm also going to remove my orange and blue lines because I'm not ready to measure them yet, measure anything yet. I'm going to leave the orange stripe and blue stripe connected to ground as is. I'm going to bring in a switch, the the the, the push button, and I'm going to connect it between pin number 2 and ground. So I have the push button going right there in the middle there. Zoom in, and one end of the switch is connected to pin 2 using that orange wire there, and the other end of that switch is connected through that orange wire there to that green wire to ground. So I actually went around to connect to ground just so that there is no crossing of wires. Um, so the switch essentially connects between pin 2 and ground. That's all it is. I also need to add a resistor between pin 2 and 5 volts. So I'm going to place a resistor of value 100k, which is brown, black, yellow, between pin 2 and high. So pin 2 is one end there, and through that 100 kilo ohm resistor, the other end is connected to this yellow wire there, which eventually goes to the power rail over there. So that's why I had those additional wires in place. Um, so that completes my um, transition from the fake switch to the actual switch. Now in this case, I want to take a look at my output on pin 3. I'll put a blue wire there, and I'm going to look at waveforms, and I'm going to run the supplies, and I'm going to run the scope. I don't need wavegen anymore. I've done that. I'm just simply going to run the scope. And as you can see, channel 2 is the output, which is reading 0 right now. And as I press the switch, and I will use this to press the switch, as I press the switch, you can see a pulse go by. Perhaps I need to make this a little bit longer so that we can see a lot more time. And as you can see there, as I press the switch, if I press and hold the switch, it'll do that. But if I release the switch, it doesn't come down back down instantly. It stays there for quite some time and then comes down. And that time for which it stays on is determined by the value of R1 and C1 that I used to design this circuit. And again, I can zoom in on the time scale here to show you how that pulse should look like at the output. As I press it, it's a clean pulse without bounce. And if I use a bigger capacitor, that bounce will be longer. So let's do that exercise really quick. So instead of a 1 microfarad capacitor that I have for C1, let us see what happens if I switch that out and put a 10 microfarad capacitor instead. So I've got, let's see, yes, I've got a 10 microfarad capacitor right here. I'm going to turn off supplies and pull out the capacitor that I have for C1, and I'm going to replace that with a 10 microfarad capacitor between pin 7 and ground. And if I switch the supplies back on and press the switch, even though I'm releasing the switch, it didn't, you see, if I press the switch and release, I moved my hand, it still stayed on for quite a long time. In this case, uh, right, so it should be over 1 second, right? So 1.1, so it stayed there for about just over 1 second, even though I release my switch. So that is to, explicitly show how this is working. Even though I release the switch, it still stays on for quite a bit of time. To make it very clear, let me set that x-axis to 1 second per division so that you can clearly see that we are doing this just about over 1 second. So right now the x-axis is 1 second per division. So if I do that, it stays there for over 1 second. So it is very close to 1.1 seconds. All right. So I hope you guys that is a little bit clear as to how the switch is getting debounced. I'm going to replace my 10 microfarad capacitor back to the normal circuit so that we are obeying the 100 millisecond as opposed to 1000 millisecond discharge time. Okay, so we have pin 7 to ground again back in, and I press the switch. Supplies need to be on. Press the switch. 1, 2, 3, 4, 5, 6, 7. Clean. Also. Okay, so that's essentially your uh, real switch data that is being used to. That's a real switch that is getting debounced. Now, the last thing that we have on this project 3, is being able to trigger the counter with the debounced switch. So what I'll do is I will zoom out of this so that I can bring in my counter circuit board that I built when we were doing the project, experiment 7 part C. We were doing the 4-bit counter. So that's the board right there that I have for the 4-bit counter. And on the left we have the debouncer, switch debouncer. So what I'm going to do is the output of that switch debouncer, which I'm measuring right now, I'm going to take that blue wire from there and I'm going to actually connect that to the input of my inverter. The output of the inverter is essentially the clock for the 4-bit counter. So only when I press the switch, I want the counter to increment by 1. And if this was a bouncy switch, if I press it one time, it is probably going to accidentally, unintentionally increment through 2 or 3 or 4 times, because it's going to see several of those clock edges, which we don't want that to happen. So that's why we debounced it. So our goal is going to be to increment that count indicated by the 4 light emitting diodes only by 1 every time we press the switch, and not accidentally move up several values. Okay, so let me give it power and ground here. I'm going to give the power through this and ground through this. So I've connected power and ground to my counter board as well. Let's switch on the switch. Supplies are on. Let's see. So 0, 3, 4. Okay. So as you can see, I still have an issue here because it accidentally incremented by 1 a few times. So I hope you guys are able to see this. The counter initially incremented a couple of times, even though I didn't want that to happen. So that went from 1 to a few. So 7 here, 8 here, 9 there, 10 there, 11, 12 is okay, 13 is okay, 14 is okay, 15 is okay, 0 is okay, 1 is okay, 2 is okay, 3 is okay. So it's kind of doing good on some presses, but it is still bouncing on the other presses. So to solve that problem, what we can do is increase that capacitor a little bit. So what I'm going to do is perhaps put another capacitor in there, maybe another 1 microfarad capacitor in there to make sure that it doesn't come back down very quickly. So let me search for a 1 microfarad capacitor, and I will put that in parallel to the one that I already have to make it effectively 2 microfarad. So I'm going to switch off the supplies for a moment and put another capacitor of value 1 microfarad in parallel with the current one, so that they both add up and give me 2 microfarad. Okay, 2 capacitors in parallel. Switch on the supplies again. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now I hope you saw the entire sequence where it never gave me that issue. Earlier it was jumping up a few presses, but now it's never doing that because we have gone to 2 microfarad. So we are staying on for quite a bit. So we are staying on, instead of staying on for 100 milliseconds, we are actually staying on for 200 milliseconds. So because we have doubled that state in which we are on, that's why it is not going down. Of course, this is not a very ideal situation because instead of going from 100 to perhaps 120 millisecond or 140 millisecond, we went all the way to 2 microfarad, so 200 milliseconds. In fact, over that, 220 milliseconds. So it's not very efficient because it's staying on for a longer time than required, which means more energy consumption on an average. So We will address that energy consumption to reduce energy consumption uh, when we meet again on Monday. But I hope you see what are the design equations that went into this. How did we build the counter, the debouncer? How did we demonstrate it using switch fake data and a real switch? And at the end, the real test was to actually trigger the counter. And when we did that, we sort of adjusted our capacitor a bit more. Uh, so I hope you all of those choices you were able to make sense of those. Okay, let me stop recording here and we will take questions.